the AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna, for introducing the session. A very good day to everyone, and thank you for joining. Welcome to AI for Good's AI and Machine Learning 5G webinar. My name is Jiaying Meng from ITU, the International Telecommunication Union. Today, we are excited to host another webinar titled Green Energy and Traffic Forecasting Using AI and Machine Learning Challenge Match. This webinar aims to introduce and explain two problem statements from Huawei that focus on the optimization of energy use in mobile networks and traffic prediction under the domain of spatial temporal forecasting. As always, we are counting on you to help create an engaging discussion. If you have any questions, please type them on the video wall and we will take them during the Q&A session right after the talk. Before officially starting the session, I would like to introduce our esteemed speakers, Nicola Pjelvesen and Tarek Sisalam. Dr. Nicola Pjelvesen is a senior researcher at Huawei Technologies in Paris. His research focuses on large-scale network modeling and optimization, green communications, and machine learning applied to wireless communication systems. Dr. Tarek Sisalam is senior researcher at Huawei Paris Research Center. His research interests lie at the intersection of machine learning, networking, and modeling, with a focus on learning with system constraints. And as always, my colleague Vishnu will be taking charge of the Q&A session. Without further ado, I would like to pass the baton to Nicola. Nicola, the floor is yours.
Hi, Jiaying. Thank you for introducing me. And let me start my slides. Okay. So today I'm going to introduce the first challenge that we are proposing. As you say, it is on green energy. And the title of this challenge is a smart energy supply scheduling. So before starting, let me introduce a bit why we are looking into this problem. And here, the network that we use every day requires some energy, as you can expect, to be powered. And here we see an example of a generic average network size that consumes around 22 megawatt hour per year. However, you know that there is an increasing cost of energy, which is accelerating the green transformation of the telecom industry. We see an increase year by year, both when looking at the electricity price, but also at the diesel price. And most importantly, our industry, the mobile industry, was among the very first ones to commit in agreement with the outcome of the Paris Agreement to reach net zero emissions by the year 2050. And this is the reason why we are looking at powering the network, as you will see in the next slide, with green energy. For instance, energy that we can harvest from the sun. And this is particularly important also because the trend of energy consumption is highly driven by the traffic demand. As you can see in this flow, traffic demand is the increase of traffic demand requires the deployment of additional infrastructure, so more mobile base stations, for instance, that requires more electricity to be powered, and this more electricity will bring also more carbon emissions. So we need to break the chain at a certain point, and we are going to look at breaking the chain between the electricity increase and carbon emissions increase, for instance. And as you see, in the past years, there was also an increase of the traffic demand. This increase is also forecasted to continue in the coming years. And there are multiple reasons why the traffic demand is increasing. The first reason is that the number of subscribers is increasing, but also the amount of devices per subscribers. As you can see in this figure, we are not connecting to the network only with our phone, but also with tablets, with computers, sometimes with TVs, and so on. And also we have new services that in particular are data hungry, like high definition video streaming, but also virtual reality, augmented reality. So we expect in the future an increase of the traffic demand. So we need to be very careful when looking at the electricity that is required to satisfy this demand of traffic from the users. And in particular, when we look at the network, we discover something that is very interesting, which is that most of the energy which is consumed by the network is consumed in a very specific part of the network, which is the radio access network. So for those that are not familiar, the radio access network comprises all the base stations, so all the antennas that sometimes you see around the city that allow our mobile phones to connect wirelessly to the core network. So 76% of the energy is consumed there in the radio access network. Then we have the core together with the data center that accounts for 20%, and then we have other parts of the network that account to 5%. So it makes sense that we focus and dig more into the radio access network, into these base stations. And today, base stations can be powered by different sources of energies. You can see this figure. We have a solar energy, so energy that we can harvest from the sun. We have a grid energy, so the traditional electricity grid. Then we have diesel generators. This is particularly in the case of rural areas or emerging countries where there is no easy access, for instance, to the electricity grid. So diesel generators are used to power the base stations, and in particular, they are used as a sort of backup when the energy is not available from the grid. The diesel generators are there to provide energy. And then, of course, we have also batteries that can be used to store the energy that comes from other sources to be used later in time. Of course, each of these energy sources have different characteristics, and in particular, they have different availability. So it's clear that the energy can be harvested from the sun only during the daytime, and also when the weather is good. And also the grid energy can be available sometimes only during certain hours of the day. And then also the batteries, they are available only when they are charged. If there is no energy in the battery, you cannot use it. When looking at the networks that are deployed around the world, GSMA has put together a nice report that tells us that in average, most of the energy which is used today to power the networks comes from traditional electricity grid. So they are non-renewable energy. And then we have a 21% that comes from renewables and a 6% that comes from diesels. Of course, each of these sources have a different impact in terms of cost, but also in terms of carbon emissions. We would like to use more renewables to emit less CO2 instead of using diesel generators that emit more CO2s. So this is, in fact, why we are proposing this challenge. And in the next slides, I will present the problem and the data that we are going to share with the participants of this challenge. So the target, the main task of this challenge is to exploit machine learning to design the energy supply strategy of a green network. So let's say that we have different types of information available. We have historical solar power generation information, so how much energy was harvested from solar panels deployed in our network site. We have also information about the weather conditions. For the traditional grid, we know how much energy can be provided by the traditional electricity grid, and we also know the schedule in terms of outage, what we call the outage plan, that tell us in which hours of the day the traditional grid will not be available. Then we have battery parameters that tell us, for instance, the initial state of charge of the batteries, the capacity of the battery, the speed at which the battery can be charged and discharged. And then we have information about the diesel generators, so how much energy can be provided by the generator. All this information should be used to create a strategy. And the goal of this strategy is to reduce the energy cost, to reduce the carbon emissions, and also to guarantee the service of the network. So we don't want an aggressive strategy that may end into a scenario in which the base station has no energy available to be powered. And to show you a bit about the variability of this data, I added some plots to this slide. And you can see that the solar energy, for instance, can be harvested during the daytime, and it is affected by the weather conditions. Here you have 2 days of data. Let me use the laser pointer, and you can see that during the first day, for instance, you harvest more energy than during the second days. And also the energy consumption, you can see that is higher during the daytime, and the grid is available only during some hours of the day. So there are some hours in which it is not available. And then, of course, there is also the battery that can be charged and discharged. When looking at this problem, the participant will need to consider the speed at which the battery can be charged and discharged by computing the state of charge change rate by using the formula that you can see in this slide, which is basically the total available energy minus the load, so the amount of energy which is consumed at time t, multiplied by a coefficient and divided by the product of rated capacity and rated voltage. All these parameters, as you will see later, will be shared with the participant. And importantly, when we have an exceed of energy availability, this energy can be stored into the battery for later use. This is the first dataset. We have 3 datasets that we're going to share. And the first one is called Site Information and Grid Outage. And this is the content of the dataset. We have in the first column site ID, which contains an identifier of the site. We are going to share information about 10 different sites. And for each site, we are going to indicate the amount of power that can be provided by the diesel generator in kilowatt. We have the capacity of the battery in ampere hour, the rated voltage of the battery, again, in volt. We have the battery charge and battery discharge coefficient, that are the coefficient that should be used in the formula that I showed before. We have the initial state of charge of the battery, so the initial level in percentage of the energy which is stored into the battery. And then we have the depth of discharge, which tell us the minimum level which is acceptable for the battery. So our strategy must not discharge the battery below this given level. And then we have the grid power, which is the amount of power that can be provided by the electricity grid. And then we have the grid outage plan, which is very important. It is an array of Boolean values that tell us the weekly grid outage schedule. So we will have 168 values, one for each hour of the week. So 24 multiplied by 7. If the value is true, it means that in that hour there is an outage scheduled for the traditional grid, which means that no energy can be taken from the grid in that hour. And if it is false, there is no issue. Then we go to the second dataset, which is about the solar power and weather conditions. Here, again, we have the site name, which is the identifier of our site. And for each site, we have days and hours. And in particular, we're going to share 60 days of data, so 2 months. And for each hour of each day, we have information about the solar zenith angle, which is the angle between the sun's rays and the vertical direction. And then we have the direct horizontal irradiance, the direct normal irradiance, and the global horizontal irradiance, both in a clear sky condition and as measured. And then we have the relative humidity. And finally, the amount of energy which was harvested by the solar panel in that hour of the day. And finally, we have the third data set, which is about energy consumption. Again, we have an identifier of the site. So we go from site 1 to site 10. And for each day and each hour, we have the amount of energy which was consumed by that site. And finally, we have the output dataset, so what should be output by the participant, which is depicted in this table. So for each site name and for each time instant, we have 3 columns, so grid, diesel, and solar, that indicate as a Boolean values if that source of energy must be used or not. So for each site and we have 15-minute slots. So this means that the participant can develop strategies that takes decisions every 15 minutes. And this means that we will have 672 slots of 15 minutes in 1 week and 10 sites. So we have a data set that has 6,720 rows. And in particular, this strategy must be a weekly strategy. So the participant needs to provide these 15 minutes level decisions for the 10 sites for an entire week. And there are a couple of notes that I've written here. In particular, when the energy provided by the selected energy source is not sufficient, the battery will be discharged to cover the shortfall. And when instead there is a surplus of energy, then this surplus will be stored into the battery. And the participant will need to provide a CSV file with the output dataset that I just mentioned, a report which describes the solution architecture, the strategy, and also the outcome of the model. So it will be interesting to see if the participant can understand why the provided strategy is optimal according to their developed models, and also the code to support their finding and the strategies. And the final winner will be determined by weighting equally the submitted solutions and the reports. So 50-50. So it is very important to write a good report if the participant want to win this competition. And this is the criteria that we are going to use to score the solution. So the participant will provide this file that describes the strategy. This strategy will be run and simulated, and we will score the solutions according to this formula. As you can see, it is a weighted sum of 4 different terms. The first is the diesel use number, which indicate the number of starts of the diesel generator. So starting the diesel generator brings some fixed cost that we want to limit. So we want to minimize the number of times the diesel generator is started. Then the second term is the diesel total time. So the total operating time of the diesel generator that we want to use for the less amount of time. The third term is the diesel max time, so the maximum continuous operation time of the diesel generator that we also want to minimize. And finally, we have the total operating time of the grid, which is indicated by the 4 terms that we want also to minimize. So this should allow you to see that if you want to get the minimum score, which means the best solution, you need to use in the best way the energy that you can harvest from the solar panel. And in particular, 2 important conditions are also that if the state of charge at any time t is below the value indicated by the depth of discharge, then the solution is not feasible and the score will be invalid. So you don't want to discharge the battery below the DOD value. And also the time that is required to generate the strategy, of course, after training all the necessary models. So this is only the time to generate the strategy after everything has been trained, must be less than or equal to 1 second. And this is the timeline of the competition. It's starting today, and it will run until September 30. And after the solutions and the reports will be evaluated during the month of October, and we will have the final ranking by November 2024, and also the award ceremony that will be held after COP29. There are some prizes, as you can see in this slide. The first prize also include the travel to COP29, so the related expenses, and then we have prizes for the second, the third, the fourth, and the fifth solutions, and 3 special prizes for the best student, for the most creative solution, and for the best presentation. So that's all for our first challenge on the green energy topic. And now let me introduce my colleague, Tarek, that is going to present the second challenge on traffic forecasting. So please, Tarek, you can take the floor.
Good afternoon. Thank you, Nicola, for the kind introduction. My name is Tarek, and I'm a researcher at Huawei. And I'm excited today to present our new spatio-temporal forecasting challenge. So this competition aims to predict traffic throughput volumes within complex communication networks. As depicted in the figure here, a network comprises of numerous beams. In reality, our dataset includes approximately 3,000 beams. And to successfully address this challenge, participants will need to develop cutting-edge machine learning models capable of analyzing intricate multivariate time series data. The dataset also encompasses diverse features, including throughput traffic, time, resource block utilization, and user count. And this will become more clear later. So a bit of motivation of this challenge is that accurate prediction of traffic volume is paramount for optimizing network flow and resource allocation. For instance, Huawei's SRCon, entitled the SRCon platform, the simulated reality of communication networks, showcases the critical role of traffic forecasting, which is the block over here, in driving downstream advancements. As depicted, traffic forecasting underpins the essential components such as user experience prediction, encompassing metrics like traffic load, energy consumption, etc. Furthermore, it informs the mathematical optimization and policy decisions, leading to the selection to optimal network parameters such as radio frequency configuration, UE association, and network topology that is used later on in deployment. So the development of highly accurate forecasting model has the potential to heavily impact traffic management, resulting in substantial societal benefits, such as energy conservation, enhanced user experiences, and improved environmental sustainability. The challenge offers high-resolution data sets with precise hourly granularity at the beam level. Beyond throughput volume, the dataset includes throughput time, physical resource block utilization, and mobile user count. Participants are tasked with the objective of this challenge is to forecast future downlink throughput volume, utilizing historical data for the downlink throughput volume, and optionally the other provided features such as the throughput time, the resource block utilization, and the number of mobile users. A bit more on the data set is that the data set is divided into a training set comprising of 4 data sets. As you mentioned, this is at an hourly scale of network performance metrics for about 3,000 beams across 30 base stations. And each base station consists of 3 cells. And each cell consists of 32 beams, spanning 5 weeks. This equates to about 10 million data points in the training set. As previously mentioned, the data encompasses 4 features: the target variable, the throughput volume, and the additional features of the throughput time, resource block utilization, and the user count. And the model performance is evaluated on 2 test sets, 1 immediate week following the training set, and a week afterwards with a 4-week gap, specifically week 5 to 6 and 10 to 11. So the submission will be evaluated through a very simple metric, straightforward metric, which is the mean absolute error, which will assign equal weights to deviations from the true value, considering about the 3,000 beams and a 2-week evaluation period at an hourly precision, resulting of a time horizon of 336 hours. Then the mean absolute error is calculated by averaging the absolute deviations of the predicted values from their corresponding ground truth values. Now, for the submission specifications, the submissions must adhere to a specific 2-column format. The first one is the ID that contains unique identifiers for the forecast values for the 2 weeks, 5 to 6 and 10 to 11, specifying the hour, the G node B, which is the base station, the cell ID, and the beam ID. And the second column is target, which should contain the corresponding forecasted downlink throughput volume. And it is just an example of the submission file that we just mentioned. So the role of the participant is just to replace these values of the target by the predicted ones. So just to give a benchmark for participants, we implemented several baseline models. These include the naive approach by historical average here, that this there is just the average traffic for a single week, and more sophisticated recent models through deep learning, such as bilinear, I-transformer, and patch transformer, and the vanilla transformer, where I-transformer and bilinear are actually multivariate time series forecasters, and the remaining ones are univariate. Just to address some key points from the discussion of the challenge, because we already saw participants were enrolled and already filling up the leaderboard. So to address common inquiries, we provide the following clarifications. If you have issues with exceeding the submission size, you can limit or reduce the numerical precision of the values that you're submitting. And participants are tasked with forecasting future values of only the downlink throughput volume and not the other features. Those other features can be used or leveraged during the training time, but the actual target is only the downlink throughput volume. We saw a couple of participants were confused about this point. And for the submission, how many submissions you can do, the submission cap is 200 entries in total, cumulative, with a daily limit of 3 submissions per participant. And the provided submission file, just to remind the participants, it is in the following format. And their role is to replace the target values with based on their forecasting methodology. And there is no starter notebook provided for this challenge. And moreover, For the test set availability, we saw a couple of participants asking about the availability of a test set. So it is a time series forecasting task. The participants are only tasked with predicting the downlink throughput volume for specific timestamps. So you can think that input figures are the actual timestamps in the sample submission file corresponding to these the weeks that we've specified, which are the weeks from 5 to 6 and 10 to 11. So thank you for your attention. That's all from my side, and we're eager to see the innovative solutions that you will develop. Thank you.
Thank you very much, Nicola and Tarek. And we can take questions now. And we have good number of questions, which is good. It is preventing me from asking mine, but let me start here. Ismail is asking reference notebooks. Yeah, so Nicola, you already know the value of reference notebooks. Are there some reference notebooks that you guys are publishing for both these problem statements? Are there some tool sets or something that you are publishing, or reference solutions the participant can start with this?
At least for the green energy challenge, at the current stage, we are not sharing any notebook. There is a reason actually why we are not doing so, and it is because, as we have also seen in the previous years, we don't want to bias the participant to any type of solution. So last year, for instance, there was a lot of work on data preprocessing, and actually the winners were able to preprocess in a smart way the data. So we don't really want to provide any notebook that takes some decision. We want to give free space to the participant to really do their best and provide any sort of preprocessing technique, any sort of machine learning method to solve this challenge.
Mm-hmm. Okay, what about you, Tarek? Are you having some reference notebooks, or I see that you're in sample submission files, but apart from that?
Yes, it's for the same reason as Nicola stated. So we're not providing a starter notebook, but we did provide some results on baseline. So the participants have roughly numbers to compare their solution with.
Mm-hmm. Okay, thank you. Then the next question, Luciano, you should also evaluate energy supply to solution generator machine. I think this is regarding maybe Nicola's problem statement, trying to add the overall evaluation energy into this solution energy as well. But let me ask Nicola, what do you think?
I think it's a good point. So for the inference time, we decided to put exactly for this reason a condition. So the time to generate the strategy should be below 1 second, which is in some way a method to control the complexity of the solution. For the training time and for the training complexity, there is not a constraint. But I think that this is something, for instance, that the participant may discuss in their report. So since we are talking about energy saving and being more green, I guess that a good report should indicate also why they selected a particular machine learning technique or that particular framework, also looking at the overall sustainability of the provided solution.
I see. Okay, thank you. Tarek, do you want to add something, or is this I don't think that's related to Tarek, right? You want to add anything?
No, I think it's fine on my side. I don't think it's related to my problem statement. Thank you.
Okay. Antoine is asking, are we looking at environment impact balance of consuming simulations of forecast, example, carbon footprint? That's a tough question. Nicola, if you would like to take that.
I think is a question which is similar to the previous one. Yes, I think that in our current times there is a need to look at the sustainability of the machine learning and artificial intelligence solution that we provide. And again, I believe that it should be a topic to cover in the report. So I expect some discussion about the complexity of the solution, which is important to do. Again, this, in the case of the green energy problem, is more related to the training. So the amount of computation that is required to train these models. For the inference time, there is a strong condition. So the overall solution should be provided in less than 1 second.
And from my side, I think it's slightly relevant to.
Yeah.
Sorry. Yeah, I think it's slightly relevant
go ahead.
to the problem statement of forecasting. So the metric that we chose is the mean absolute error. So it's not directly linked to the carbon footprint or what's the potential environmental impact of it. But just to simplify the evaluation criterion is that we just went ahead and selected this metric.
Okay, from my side, about running this strategy, I think, Nicola, you mentioned during your slides that for evaluating the submissions, you would run the strategy. Can you explain what does that mean? Especially, you just now mentioned about the 1 second timeline, right? So what is that? How will you run the strategy? And how will you evaluate such conditions?
So what happened is that the solution which is provided by the participant describe a decision to take every 15 minutes in terms of a source of energy that should be utilized to power the 10 sites that are in our data. What we will do is to take this solution and it will run in a sort of a small simulator where there will be 1 week of data about energy consumption, about solar harvesting, and all the required processes. And at the output of this small simulation, we will have the 4 targets that are in the score matrix. So the amount of time in which the diesel generator was used, the amount of time for which it was started, which depend on the provided strategy. And the score metric will be computed into by using these output parameters, and then the participant will know how the strategy performed. And so they will have in the public leaderboard first value, that is the accuracy, how good is their provided strategy. So we are required to do this because we don't really know which is the best strategy. So this is not a typical problem in which you have the ground truth. The ground truth is not there. What we can do is to simulate the strategy, see how the network performs with that strategy in our simulator, and compute a score function based on that. And yes, so what the participant will need to do is to learn from these 2 months of data that we provided, learn how the solar energy harvesting behave, how the different sites consume energy in different hours of the day, but also how the consumption is different in different sites, and use all this information to create their best strategy.
Great. Okay, thank you. Dr. Kaita is asking, are the base stations in traffic challenge in proximity to one another? Yeah, I had some questions related to that for Tariq as well. But let's take this. The base stations locations, Tariq.
All right. Yeah, that's a good question, and it's a chance to clarify this further. So basically, the data is generated assuming that the base stations are within more or less the same city. But that's information that we don't provide. So it's up to the participants to identify those correlations. However, there is an implicit adjacency information that is contained within the identifiers of the beams. So basically, beams sharing the same ID for a cell, it means they belong to the same cell. You know they're adjacent, as well as cells having the same ID for a base station or the G node B. You already implicitly know that they are assigned to the same base station. And I hope this answers your question.
Cool. Yeah, thank you very much. Yeah, I think that's an important information. So maybe I can ask a follow-up question about that. It is okay for the participant to use this implicit information in the predictions, right?
Definitely, yeah, that's part of the challenge. So it's up to the participant to identify these hidden relations.
Thank you. Julius is asking, is a report for spatiotemporal beam prediction necessary? I would say yes, but Tarek, please.
Yes, there is, but to the best of my knowledge, I think it's for the winning solutions. But I recommend the participants to read the submission page. I think it contains all this information for on the submission guidelines and so on. But normally, yes, there should be a report that is explaining what methodology they took, and of course, this methodology needs to be reproducible.
Another question maybe for both of you. Normally we get is whether this is real data from the network and whether or whether it is simulation plus real data or only simulations. So can I ask you both, maybe Nicola first, what is your answer?
So for the green energy problem statement, the data is synthetic data, which is generated, of course, not randomly, but based on some realistic behavior that we may experience in the network, both in terms of energy consumption and in terms of solar energy generation.
And for the traffic forecasting, it's basically the same answer. It is synthetic, simulated, but with parameters that you'd see in a real network.
Thank you. Can I ask you, Tarek, do you use SRCon for simulating this?
To the best of my knowledge, no. But one of the motivation of the challenge is SRCon. Thank you for that question.
Okay. Yeah. Thank you. Maybe let me ask Nicola about the score. So I think your score strategy should be to minimize it, right? If I understood your score right, it should be to minimize it. Okay, and the solar, yeah. So the solar does not show up in the score at all. Why?
It's true, and in fact, the score only consider the diesel in 3 different terms: number of starting, duration, and maximum duration. This is something that we want to reduce, as I was saying, because starting the diesel generator has a fixed cost, and the duration means that we emit more CO2, right? Because it's the most, among our sources, the one that emit more. And also the maximum that we want to limit because we want to reduce the probability of having a fault in the diesel generator. And then the last term is about the traditional grid that we want to minimize in time. It is true that the solar energy does not appear, but it impacts all of these. So you need to use smartly the solar energy. And when I say smartly, means using it both in time, but also storing it into the battery by taking the right decision. If you want to minimize the amount of time the diesel generator is used and also the amount of time the grid is used. So let's say that the solar panel, the solar energy is the proxy to impact the diesel usage and the traditional grid usage.
I see. I see. Okay. Okay. There is Evren is back. Thank you, Evren. Evren is asking a question. Do you have an essential baseline model for second problem statement? Maybe we can confirm our solution at least for some models in terms of accuracy. Yeah, Tarek, for you.
Thank you for that question. I think we're not providing the actual trained models, but we do provide the accuracy that the inaccuracy that they attain in terms of the mean absolute error. And I think it's nice to, I suggest for the participant to go and check those numbers and see where they're located in the leaderboard, because I think the historical average is like 15. So at least you should beat that. So I think that's pretty much my answer. Thank you.
Okay, thank you. Maybe Tarek, while you are here, the direction of the beam. So do you worry about the direction of the beam at all? I see that the data set does not contain it. I at least I don't see it here. But can you please, does this make a difference at all, or do you plan to do it later? Let me just cross check. No, I don't see it. So yeah, so can you comment on the direction at all? Does it make any difference at all, or you want to take it at a later point in time? What is the role play?
That's a very interesting question. Yes. So we don't, if I understand correctly, the question whether we provide the engineering parameters and this important engineering parameter being the direction of the beam. And we don't, but it's implicitly there. So basically the beams labeled, let's say 0 up to 30, the beam 0 in a different cell would share the same engineering parameters. So that's information that the participant could leverage. I'm not sure if I was 100% clear.
Okay. I get it. Okay.
Yeah.
Yeah, that's
so beams having the same order of IDs would share the same engineering parameters. However, we're not providing engineering parameters. It's up to the participants to figure out these correlations, and actually may not be even the participant. Maybe the machine learning model is sophisticated enough to identify that in an automatic way, and that would something would be nice to see.
I see. So yeah, this is another implicit info that you have hidden. Yeah, okay, I see. But I think your alignment in terms of the sequence of the parameter that remains the same across the data. That's what the beam. Okay. That's interesting. Let me just note it down. Okay, yeah, thank you. That's quite interesting. I want to ask Nicola about his time window of the data set. In fact, that's actually very interesting time window that you have. Data set 3 is on a daily basis, if I understand right. Data set 2 is for 60 days, if I understand right. And I don't know whether it is daily or not, but you have it for 60 days, that's for sure. Data set 1, I'm not sure what is the time window that you have. Maybe you can clarify. Output data is 15 minutes window. This is quite interesting. Why do you have this, and what is the significance of it, and what should the participant make out of it at all?
Okay, so let me clarify. Thank you for the question. So the first data set is the one about the site information. It contains one row per site. So for each site, we know all the parameters. And it is true that it also includes the grid outage plan, which is a set of 168 values. So one value per per hour of the week. So you know for each hour of the week, and this is all true for all the weeks, at which time the grid will not be available. So this is the first one. Then the second data set is about the solar energy generation. So here we have 60 days hourly values for each site. So for each site, we know in each hour of these 60 days, how much energy was generated. And then for the third data set, which is about energy consumption, is the same for each site. For each hour of these 60 days, we know how much energy was consumed. Then for the output, we have for each site, we want to provide a weekly strategy. So the strategy will cover only 1 week, but the decision can be taken at 15 minutes level. So it means that we have 4 decisions per each hour. And this is to give to the participant more flexibility in their strategy. So in the same hour, they can use 4 different or change 4 times the source of energy that they selected as the best one to use in that hour. For instance, they may decide to use the solar only 50% of the time and then use the traditional grid. So this gives more flexibility to the solutions.
That's great. Yeah, thank you very much. And then let me ask you quickly one follow-up question. The alignment, the timing alignment between the 3 data sets, can the participants assume that they are aligned, or that does not matter, or what is your comment on that? Do you have some hidden figures, hidden correlations like Tarek, or what is your comment on the alignment between the 3 data sets?
We can say that they are aligned. So the data set about the solar energy generation and about the energy consumption, they are aligned. So they have about 60 days, and they can assume the first day to be a Monday. So this will allow them to match with the outage plan that is in the parameters in the first data set. And yes, and then when they provide the solution should be a weekly one. So the first instant of time should be, the first day should be a Monday, the last one should be a Sunday, and again going from midnight to 23 as the other data sets.
Thank you very much. Yeah, I was quickly noting down. Julius is asking about transformers. I think Nicola already answered this. I mean, you guys already answered this. I think it does not matter, but no bias. So let me ask you: do we need to use transformers to win?
No, not really. I think what they noticed that the baseline list that we provided was mostly transformers. And there is a reason for that, because they're the SOTA for long-term time series forecasting. So we just had that preference to put a couple of transformer models, but of course there is no constraint to have a solution within the transformer family, so they can try out whatever model they want.
Thank you very much. Maybe let me ask on the resources and the size of the data sets and the compute which is required. So of course, before I ask, I have to tell you that I have to tell the participants that ITU provides compute, GPU compute. So if you are registered for the participation, please let us know if you need GPUs. Free of cost. ITU provides free compute GPUs if you are registered for any of our challenges. But Nicola, what is your data set size, and do you, in your reference solutions, do you see it takes a lot of compute and time, or what is your feedback on that?
Well, the dataset size is is not that big. We are talking about thousands of entries of rows, so we are in the order of a few megabytes. And for the computing, it actually depends on the algorithm which is used to solve the problem. So it's possible to solve it by meeting the constraint that we provided. And of course, again, depends on the trade-off with accuracy and of the provided algorithm. So yes, much depends on the algorithm that is selected by the participants. And also, I want to remind that this is not a classic machine learning problem in which the ground truth is no. So you don't really know if you are really at the optimal or not. So this may not be possible for the participant to understand if their solution is optimal. What I suggest to do is to try with the data. We decided to share a lot of data, 2 months of data, because I believe they can take a part of this training data, split it, and try to see how well what they develop with a portion of this training data can be adapted to the remaining portion. And then this should be the strategy, the approach they use to then generate this weekly strategy that we will test, of course, on other data that we have that was not shared with the participant initially. But still, yes, much depends on the approach that they select.
Okay, interesting. Tarek, please.
And for the traffic forecasting challenge, it's slightly different. So we don't impose any constraint on the inference time or the size of a model. So the participants have the freedom to have pretty large models. So it's up to them and their training budget. And hopefully having a large model leads to better accuracy, but it might not always be the case.
I'm just curious, Tarek, how big is your 10 million data points?
In terms of the size, like in gigabytes? I think it's about, if I'm not wrong, it's around 200 megabytes, so it's not that extreme. So it's still manageable. Yeah, so that's the number of data points. So it's 10 million for the training and about 1 million for the test. So about 10%.
Great. Okay. Thank you very much. I think we are kind of close to the time. I want to thank both of you for taking the time to patiently answer all the questions. And there is Jang. Back to you, Jang. Thank you very much.
Thank you so much. Thank you so much, Vishnu, for the Q&A, and Nicola, Tarek, for your contributions during the whole session. At this point, I would like to thank everyone for sparing your valuable time to join the webinar today. We have more sessions in the future, so please check the AI for Good program page for the details. Please also know that the challenge is now open for registration and participation. The link for registration is posted on the video wall. You can start working your solutions already and submit the results on the portal. Several prizes, including certificates, are planned to be handed out to winners of the challenge. Details are on the challenge webpage, so please check. And as Vishnu has already mentioned, we are offering computes with GPUs that will be provided to the participants based on need. So we look forward to your participation and submission. Thank you for joining and have a nice day.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Thank you.